Hello, everyone. Today I'm going to give you a presentation about the limits, the horizons that we have currently in front of us that generate probably the large size of the challenges that we need to deal with and how potentially the evolutionary testing can solve this for you. So first of all, what kind of horizons are we talking about? So just to give you a couple of several examples, one that I can give you is big data. As you know, big data is a concept which basically describes the fact that we are dealing with increasing size and breadth of information that we need to cope with. And it's constantly being analyzed and sliced in different ways. It's basically a dynamic and changing environment with a lot of challenges in terms of how to deal with the amount of data and the possible interpretations of it. Another challenge, which I'm not really sure whether someone pays that much of attention currently, but this is the trend of whatever as a service, as I call it. This is basically the desire to expose existing and new functionality as a service in order to enable a more dynamic user model, but at the same time you're often in a situation where basically you know what the service is supposed to do, but you're not really sure how exactly, and in some cases it's hard even for the vendor to actually describe what actually happens. It could be a moving target, so it's not always clear. A third example that I can give you is agile delivery and user experience. The previous lectures that were held in this hall actually talked about this. So this is actually the continuous cycle in which we develop and deliver functionality to the end user, and this basically creates an environment which is constantly changing, and although in many cases we are able to use the same kind of functionality and achieve the same goal, it's not always the case that we do that in the same way or use the same underlying technology in order to achieve this. And finally, as an example, you have heard a talk about Internet of Things, and probably you are already aware of the process of this happening. This is basically the fact that everything goes online. And this creates insane amount of data sources, data sinks which consume this kind of information, a large number of connections, and basically a very complex environment, which again provides a challenge for a person that wants to test or assess this kind of environment. So why evolution? Basically, the answer is because the evolution is able to deal with a large complexity with very simple setup. And here I have thrown some numbers that are supposed to convince you that this is true. So just to give you a parallel about the scale of what we are currently dealing with in the domain of IT and what the biological evolution is dealing with. For example, in terms of networks, the internet is estimated to have approximately 2.4 billion users and 14 billion nodes which are communicating between each other. And as a comparison, we can give just a single instance of a human brain, which has approximately 86 billion neurons and about 1,000 billion connections. So you can see that the complexities are comparable, and biological evolution actually exceeds this just with a single instance of a system that it deals with. In terms of data volumes, you can see that there are several examples of, for example, the amount of internet traffic that is estimated to happen daily, which is approximately 1 petabyte per day. You can also see that, for example, eBay is dealing and maintaining with 80 petabytes of database. And at the same time, on the other end, biological evolution is actually dealing with, for example, just for humanity, we have approximately 7.2 billion people, and each person has approximately 1.44 gigabytes of genome, which in estimate gives us 8.76 exabytes of operated data each second. And this is just for humanity. We have additional estimates for several tens of millions for the actual species that the biological evolution is dealing with on Earth. And as you can see, both environments are quite complex and are dealing with similar amount of data and complexity. So some details. Do we have a problem? Okay. So some details on biological evolution. I'm sure that most of you are aware of this, but I just want to level the playing so that we can later on introduce the terms and the comparison between the evolutionary testing and the actual biological process so that you can have more direct understanding of what we're trying to present here. So first of all, what is biological evolution? It's relatively simply to describe as a process. It's the process of adaptation of biological population to its environment through survival of the fittest and through inheritance of properties between successive generations. This was formulated as an idea in straightforward terms by Charles Darwin in 1859. And the book is called, or referred rather, as Origin of Species, but it has quite a long name, as you can see, which was the trend there. And this book, if you're interested, could be viewed and read online, together with some materials related to it, on a couple of sites, which are displayed here, darwinonline.org UK, and also it's available for free on Amazon Kindle and Apple iTunes. So, with regard to biological evolution, where and who is involved in it. So first of all, we have an environment which is inhabited by a population of individuals. And also we have a population which consists of generations. And finally, we have generations which consist of individuals, which is illustrated by the cats here. As you can see, they're grouped in generations, and they together form a population which is placed inside the environment. With regard to biological evolutions, we had another aspect of it, which is the relationship between templates and instances. So first of all, a genome is what describes and can produce population and its features. So this is illustrated by the grayish DNA and the grayish figure of a cat. Then we have a genotype, which describes and can produce an individual and its features. So this is illustrated by the cohort cats. As you can see, each genome represented by a different cohort has different properties and generates different properties in the individuals. So having in mind this kind of relation, we can actually postulate that the genotype is the instance of a genome, which is very important into actually constructing a model of the evolutionary process. So additional aspect of biological evolution, survival. So what is survival? This is the process when an individual is fit and survives if its properties allows it to adapt to the environment, which is illustrated again by this picture of those cats, where we have two instances, two cats, one which is better adapted to its environment in order to blend in, and the other is actually popping out. So if you have certain kind of a situation where the adaptation to the environment plays a role in the survival, then you will have a surviving cat at the top, but that cat at the bottom. So finally, what do we need in order to describe the biological evolutionary cycle in order to basically describe it as a whole? So first of all, survivors reproduce and create new generations. Parent genotype and its features are copied and inherited by the children. And change into a genotype or the description of an individual could happen for two main reasons. One is called mutation, which is a random change in a genotype or the description of an individual. And the second thing is recombination, which is a change into the structure of the genotype based on the rearrangement of the genes of its parents. So a gene basically is a part which describes a certain feature in the overall genotype. So basically, by rearranging them, we can achieve different kind of combinations of features into the children. And finally, which actually closes the actual cycle, is that the children are becoming are taking places of the parents, and thus are closing the cycle and repeat the cycle of the parents. So this is illustrated by this graph. You can see that here we have all of the components that we talked about. First, we have the fitness and the adaptation to the environment. And after it, we have the process of survival, in which we have individuals that are surviving, and we have also individuals that are not so surviving. And then the surviving individuals are becoming parents. So they donate their gene information, the genotypes, and through copy and recombinations, we are producing new versions of the genotypes which are becoming the child genotypes. And there could be a random event, which is a mutation, which can change some part of the description of an individual. And then through the process of instantiation, we can have children. And as you can see, we kind of try to illustrate this by producing cats which kind of have the same characteristic as their parents, but they're kind of combination of all of their properties. So what are the results and the effects from the biological evolution? Several examples which are quite important for our case. First, we have the process of natural selection, which means that better fitness basically means that whenever you have it, you have better chances for survival and production. Additional aspect is adaptation, which means that natural selection as a process guarantees you that each successive generation will be better adapted to its environment than the previous generation. And finally, the fact that we have robustness of this process, which means that evolving population and the natural selection process, although could be quite different in nature, don't need to know anything about each other, and the evolution will occur regardless of what's actually happening and what kind of implementation exists for both sides of this process. So finally, as a final thought, basically you can see that biological evolution can generate and handle extreme complexities with very simple setup. This is something that we stated initially, but here we have this demonstrated. So keep that in mind where we go into our next session, where we try to introduce the idea of how this could work in terms of testing as a strategy. So first of all, how can we describe evolutionary testing as a concept? It's basically an iterative organization of software testing in which we mimic biological evolution as a process and structure. And through this, we target and can handle very large complexities, regardless of whether we are talking about scenarios or system behavior. And also, we can handle lack of knowledge about the tested system. This is something that could be very useful in some cases, especially in the cases, especially in the examples that I gave you initially, dealing with large portions of data, services that you don't know complete knowledge about, and stuff like this. So how this can be achieved? What we need to do basically is to have a well-built test automation, which means that you need to have a clear sections of your framework which are equivalent to a test driver, monitoring, reporting, test environment management, and this should be fairly consistent in order for you to have an easier time actually implementing the next part, which is an additional layer of organization, which actually implements this cycle and the way the test cases are generated and managed through the whole cycle in order to implement evolutionary testing. So just to give the parallel between the biological evolution terms and how this can translate into an actual IT environment. So here you are seeing an example of an environment, which basically is something I believe quite familiar for everyone. Here we have a test case, which is passed to a test driver, which then generates a test input, which is passed to SUT environment, which consists of environment management and a test system, and which then, after an execution, are producing a test log, which is our test output. So in order to continue with this parallel, basically in order for evolutionary testing to work, we can state that the test case is a genotype, which basically describes an individual, which is a test execution. So having this kind of abstraction over this process gives us possibility to tell that the test case or the genotype is describing the individual, which is the same case as with biological evolution, and also the individual itself is an instance of a test case, which is also matches the idea of biological evolution. So nothing really complex here, but it's quite a straightforward relation. And continuing further, we can actually postulate that a population is a set of test case executions or individuals, as we already label them. And also, if we have a test case template, it could become or could be used as a form of genome, which can actually generate different genotypes or instances of test cases. So in this case, you could, for example, assume that you could have some formal or informal definition of a business process or something that you could use as a base to actually create an actual test case. And as formal as you get, in a better situation you will be. For example, this could be BPMN or BPEL, some kind of description, or some kind of other type of formal description from a test case management system or something like that. So continuing on, here I want to give some more details and examples in terms of what genome actually means in this kind of situation and how it can work for you. So as I mentioned, a genome is a template for a test case. So actually you can imagine that you could have, for example, as it is the common case, to have an XML or some kind of other structure, a representation of the template, which describes its parts and how they are related. For example, a number of, let's say, methods and type of data that could be used in a test case. And through some kind of transformation, here I have postulated XOT, you could actually create a test case XML, an instance of a test case XML. And you can create multiple instances of them. So by this, creating from a single template multiple genotypes. So the other part of the properties of the genome and the genotypes themselves is that they need to comply or define some kind of methods that could equal a reproduction process, which again is illustrated here. For example, you could have a couple of test cases which are described by their XML. You can execute them, and for some reason, if you decide that you want to create a successor of those test cases which combine in some way their properties or the way that they're operating with your tested system, you can use some kind of transformation. Again, I have postulated XOT, but it could be something different. And you can create a follow-up XML, which could be used as a child genotype. So basically, you have, again, a relationship similar to parent and child in this case. So coming to the actual processes that can produce children from their parents. The first one is recombination. This is something that we talked in describing the biological evolution, but here I just wanted to give an example of how this can actually be implemented on a somewhat abstract level. So first of all, recombination is, in this case, means that one or more genotypes could be transformed by some mechanism into a new genotype. And usually this is based on the postulation that we use separate generations. So for example, if you have a set of test cases which you have executed in your test environment, you can label them as parents and then use them by recombining them in some way to produce a new set of test cases that could be beneficial for your case. So here we have two examples. One is I try to basically visualize a structured data which represents our test case in the first example. So we have two parents which have 3 nodes, each containing different type of data. And through recombination, we can actually exchange parts of those descriptions in order to create a child. So As you can see, in our case, we have the first node from the first parent, we have the second node from the second parent, and it could be not only just swapping elements, but also could be some kind of calculation or more advanced transformation. For example, in this case, we have the data from the third node of the first parent plus the data from the second node of the second parent. You could actually have a lot more complex structure of the genome. So, for example, here on the second example, we have a structure which basically represents a sequence of actions which are paired with data that's necessary in order for action to occur. So you could kind of imagine that this is kind of a test case which could have successive steps which are executed based on those parameters. So again, we have parents and children, and as you can see, with more elaborate structure, you can have a more advanced and free rearrangement of the elements of the genomes or of the test case elements, but again, it should be defined in some way, and this way should be meaningful in terms of what you're trying to achieve with the test case. For example, if you're trying to, for example, to keep a specific sequence of actions, probably it doesn't make sense to exchange the order of the actions. For example, if you're trying to log in into a system to do something and log out, it could be the case that it might be useful for you to change the order, but in general, if you don't want to change the order, you just want to change the data, you can actually keep the actions the same and just exchange the data, or to simplify your case, you can just go to the first example and use it and keep the structure static in your case. So the next operation that we talked about in the evolutionary process is mutation, and here this basically means that we introduce a random change with a certain probability, depending on the structure of your test case, random change into the data and the structure of your test case. So as you can see in this example, we have a certain structure of actions and data which is paired with it, and after a mutation, we actually get in the third action we have changed data. It could be a reference or a particular instance of a data that could accompany action 3, or we could change the action, or if we want, we can change both, of course. So a different aspect, which is probably not so clear in this case, is the fact that we need to define a goal and a fitness function, which basically serves as a criterion in order for us to create some kind of equivalent of natural selection. So first of all, goal definition. This is basically the idea of where you want to go with your testing, some kind of test strategy. For example, if you're talking about a certain application that in certain cases has a specific type of data corruption or exception, for example, this is your goal. You want to achieve this. So the fitness function is the formal expression or a formal method that could actually give you a single number estimation of how close you are to this goal. And this is illustrated here with this kind of graphics that we have. First, at the start of the life cycle, we have a test case which gets executed, and then we have the test case, the genotype, and the test log, which is part of the test case execution or the individual that we are interested in. And through the evaluation process with the fitness function, we can actually assign a value of this individual, which basically means how valuable this result is for us, how close we are to actually achieving a data corruption or a certain kind of error in our application. This usually is pretty straightforward process if you are familiar with a particular test case or how your application is working, because then it will be quite obvious of what you should monitor and how you can construct your fitness function. This is something that we'll discuss a little bit later. So in order to close the cycle, in terms of evolutionary testing, we already described the parts that are used in order to construct it. So first of all, if we have a set of test cases and we execute them and then we evaluate their results, if we find that their fitness, their evaluation by the fitness function is suitable for our needs, because usually from the fitness function itself, you could estimate what kind of fitness are you expecting to be sufficient for your case. Then we can stop the overall cycle and use this set of test cases, this generation, as our final solution. But if this is not the case, then we can select certain members or certain instances of this generation. Usually, we are selecting the ones that we evaluate as the best based on their fitness, and we can use the reproduction methods that we have defined for their genome in order to produce through recombination and mutation a new generation. And finally, the new generation that we have generated through reproduction becomes the current generation and goes through the same cycle. So basically, you're executing again, passing through the same pipeline, the new generation, and it becomes the current. So this is illustrated by these graphics. So initially, we have either a genome or known semi-solution to our goal. And through random instantiation or seeding, basically creating an instance of the known test case into the initial generation, we have our first generation, which gets executed into the follow-up stage, and then it gets evaluated. If we are satisfied with the fitness that we're getting, we can stop the process and basically use this solution. But otherwise, we are proceeding with selection, so you can see that we actually select some of the test cases and their results, and some of them fall off from the evolutionary testing process. And then by using the reproduction process, we are creating a new generation, which then becomes the current generation, and we are continuing with the process until we are satisfied with the results, or we have a stopping condition, which basically stops the overall optimization process. So some additional details with regard to how this whole organization is working and what is important in terms of details and properties of those components. Here I want to mention what means to have a good versus bad fitness function. So basically, the selection depends on the fitness function in order to differentiate between the different test case executions and give you an idea of which is good for your goal and which is not. So here we have two examples. The first one is with a smooth function. As you can see, if we assume that those vertical lines are basically the single instances of the output of our system. Of course, this is a very simplified example, but you can imagine that you can actually have a multi-dimensional case. But in this case, you can actually see that the intersections of the first graph and the vertical lines are quite clearly differentiated. And if you want to tell which is better than the other, it could be quite easily done. And the second case, for example, this could be an instance where you just monitor for a certain kind of exception which occurs under certain conditions. You can see that this is considered a bad choice because the probability of this occurring could be a certain value, but until you achieve this, you don't have a clear answer how close you are to actually achieving your goal. So you can imagine this extreme case in which your generation, your executions are actually evaluated with the same value, basically because you don't have a solution which actually hits the actual problem, which will be usually the case with your initial population. So basically, this doesn't give you any idea how to continue on, and the only chance that you get is by actually implementing mutation and recombination to actually hit by random chance this peak. So this is an example of something that it's good to avoid actually in your practice. So another example, which is again related to the fitness function and how the results are distributed. The SUT execution results are distributed compared to the fitness function. You can see that in the broad variance example, we can actually sample and have an idea of how close we are in the whole population to to our goal in a much better way than with the narrow variance, where we have a concentrated output in a single place of our fitness function. So in the case of narrow variance, it's not that we won't get to our goal, but the possibility for us to interpret the results and drive the evolution in more efficient ways, more limited, and you probably will need more iterations in order to reach your goal. And this usually means more time, more resources. So in general, we would prefer to have at least initially broad variance, and after we have a general idea about where we want to go with it, to have a smaller variance in order to for us to nail an exact solution or a test case that reproduces our problem. So at this point, I would like to give you an actual example of implementation of this kind of approach. It's not very detailed, but that's for the reasons of explaining this in this format. If you're interested, I can share a lot more details afterwards. So basically, just to give you first the context in which this was implemented, the SUT interface that we used is basically a set of interlinked pages which contains a number of action buttons which are arranged into a table-like format, and the content is loaded from a predefined library file at startup of the application. And this SUT, this platform, basically operates on both desktop and mobile. The automation, which we mentioned, is a key part of the ability to actually implement such an approach as evolutionary testing, is based on Lua scripts, which drive Lua to C++ binding into the SUT. The C++ was the language of choice for implementing the SUT, and the Lua was implemented basically as an easy way to actually have a structured scripting into the application. The monitoring was implemented natively into the application. It basically could, if desired, to generate a very detailed log on the actual actions that are defined into the Lua scripts, and so basically it provided a very detailed feedback on what actually happens into the SUT. And the actual problem, the goal that we are chasing in this case is that after basically prolonged use of the SUT on the mobile platform, which was the main use case for this actual application, it could happen in a week or two, probably. So you can imagine that it's a complex case. A data corruption occurred, which resulted either in missing or corrupted content on the pages, or inability to load the library data file at all. So during the investigation, we were able to not only register this kind of problem, but also the fact that this kind of event was preceded by a certain number of errors and exceptions that we were able to capture for our monitoring. So basically, we have all the necessary components in order for us to implement evolutionary testing in this case. So what implementation details I can give you with for this particular case. The evolutionary testing was implemented by using a pre-existing framework, which basically has the basic skeleton and structure and concept built into it in order to actually implement evolutionary algorithms, which is named evolutionary objects. And also we used the existing automation into the SUT. After we have implemented to a certain stage the evolutionary testing process, we actually saw that the execution on the mobile platform is significantly slower than on the desktop. So this pushed us to examine whether the execution on the desktop could be a viable solution to speed up the overall process. Basically, based on the fact that the SUT code was the same on the mobile and the desktop platform, and also the implementation that we used for the overall evolutionary testing in terms of organization of the cycle, the way we instantiated and manipulated genotypes was the same. we were expecting to have at least similar results. And in order to validate that, our plan was that after we complete the whole set of evolutionary testing and we have the final generation with optimal fitness for us to take the best individuals and the worst individuals from this generation and replay them on the mobile platform, which, although slower, would give us an idea of how the actual process of execution is happening, because we are basically replicating the same kind of execution on desktop and the mobile, and through the fitness function and the data that we are collecting in the execution work, we can actually compare whether we have the same kind of process going on desktop and the mobile. And lastly, but not as important, by doing the testing on the desktop, we were able to actually use a standard virtualized environment and have multiple instances of the evolutionary testing framework running, which allows us to distribute the execution and actually have the results even faster than what we would theoretically be able to do on the mobile platform. So to give you an example about how the scenario genome was structured, here I just want to mention that you could go really complex in this area, but for example, you can use some kind of meta language in order to describe the structure of your test case and do some to define your grammar or some kind of semantics that you can use. But what we decided is to keep it really simple, and what we did is to actually create a sequence of actions which is based on clicks in the geo, and this kind of test case structure was described in an XML form where we had two separate arrays of equal length, and in each array, the first array contained an index mapping to a Lua function that we wanted to execute within the SUT, which in most cases was clicking on a certain geo object with X and Y coordinates. And the second part, the second array, contained basically the coordinates that we want to click on, and they were represented in the natural form with integer numbers. So nothing complex here, but still it worked very well, as you will see in a little bit. What kind of data we have monitored? As I mentioned initially, creating a fitness function should be done in such a way that it should be as smooth as possible, because this gives you a possibility to actually steer the process and give and for your process to get a better idea whether it's doing good or bad. So we actually monitored quite a number of parameters, which is the number of scenario steps that we were generating, the total execution time, the number and the type of software exceptions that we were getting, the maximum memory footprint of the SUT, the number of allocated memory fragments, which was also, through our analysis, considered to be related to the problem that we were getting, the number of invalid steps, because through the randomness that this process has, some of the steps that were generated and the sequences that were generated were not valid, and the number of corruptions that we can register in the data file. Something that I forgot to mention here, probably you're wondering if the interface that we describe here, which is a number of IntelliJ pages with an action buttons, it doesn't seem that exciting and complex, but the fact is that the SUT actually allowed some of the actions to be an actual editing, creation, or deleting action. So basically, depending on the scenario that you want to do with a certain data library, you could end up with something completely different from what you started with. So that's the reason why we are monitoring the memory footprint, the size of the library file, and all of the other things. So to give you an idea about how we constructed the fitness function, basically you had, on the previous slide, you saw what kind of data we are monitoring. So basically each of those events generated a stream of values, and for each event in this stream we assigned a weight, and then basically added them together in order to achieve some kind of estimation of how close we are to our goal. And also the weights that we chose for this process were based on statistics that we got from previous executions and our knowledge and experience of the testing of this particular SUT. So here we have kind of a representation of what the fitness function looks like. So I can assure you that it actually looks a lot clearer in Java, but you wouldn't be able to actually read something like this here. So it's actually very simple. First of all, we have sum of the weights of the events that we registered into the test execution log, which are of general nature. For example, the number of steps, the footprint of the environment and stuff like this. The second component is the weights of the corruptions that we achieved or the events that we consider to be related to corruption, for example, so certain kind of exceptions. Again, we have the sum of the weights, which is strengthened by multiplying them by the library size. And also the last component is the memory footprint, which we talked about, which is actually contains an additional sum, which is the sum of the invalid actions. So basically, it being at the bottom is actually a way for us to introduce a penalty into the fitness function, and this penalty actually gives a lower fitness to test cases which have invalid steps. So this is an example and a graph of how the things developed for us when we were running this kind of evolutionary testing. As you can see in the beginning, we have a lower value of the fitness, and gradually it increases and reaches a plateau. And basically, whenever we reach the flat part of this graph, this means that the evolutionary process have exhausted its possibility to improve further. And this could mean two things: either you have reached your solution, the one that you really want, or that the parameters of your evolutionary testing are not sufficient to actually generate further improvement. So after you receive such results, it's necessary for you to do some kind of analysis, but usually it's quite clear whether you have achieved your goal or not based on evaluation of some of the results that you're receiving. So here we have a short graph which describes or basically displays how the executions of the individuals on the desktop compares on the mobile platform. As you can see, we have quite a close match of the fitnesses that we are getting in both cases. So basically, this is a confirmation that it actually paid off in a good way, that we actually speed up the execution, and we have a confirmation that the results are the same on the desktop and the mobile platform. Lastly, not lastly, but as last part of the example, we have a quick comparison of the standard analytical approach to the testing of this problem and the evolutionary testing. You can see that the standard one took between 8 to 10 person-months, while the evolutionary testing one took about 4 person-months. And in the first case, we were not able to produce any stable scenario in which we could actually reproduce the problem and debug it, and because of that, we were not able to create a fix for it, although a lot of improvements have been made. While in the second case, we had, in the last generation that we got, we had a scenario which was quite stable and was able very easily to reproduce the problem through the automation that was introduced, and this enabled a very straightforward debug and fix of the issue. So to go quickly through the pros and cons of this kind of implementation, first of all, evolutionary testing tolerates limited knowledge of the SUT, which is something that we are increasingly need to deal with. It also can work with goal-oriented test definitions. So basically, in some cases, you are forced to work with something that's not related directly to what you're experiencing into your work with the system that you are testing. This could be a business requirement or some kind of user experience that you want to achieve. So this is also very useful in this case. The third item that I have here is the ability to mass produce test cases and solutions for the problem that you're chasing. Again, as mentioned before, we can run a lot of test cases in parallel. So regardless of the fact that we are mass generating test cases, we also have the possibility to execute them in parallel, which gives us a possibility to be in a better position when we are comparing with the classical approaches. We are able to seed actually solutions into our initial state of the evolutionary process, which could speed up significantly the achievement of a result. So, for example, if you have a solution which is close to what you want to achieve, you can actually use it, and through the methods that evolutionary testing provides, to actually multiply it in different ways in order to explore the area around this test case in order to achieve the goal that you are chasing. And also, we have the guarantee that the evolutionary testing if the evolutionary testing is convergent, that means that your fitness function could actually drive you toward your goal. Each new generation that you have is a better solution to the problem that you're chasing compared to the previous generation. So even if you have to stop before you reach your end state, your plateau at which you're certain that you can't optimize further, even if you stop before that, you'll be sure that the test cases that you are getting are going to be a better solution for the problem that you want to solve. And last but not least, you can actually reproduce a very complex lifelike test cases, which are not easily done with other methodologies. So this is also something that's very useful and could be used as something that could generate benefit for you. So what are the drawbacks or the cons for this kind of testing? First of all, you need to know and understand what the evolutionary testing is and how it works in order to implement it successfully. In order for you to, for example, if you are in the case where you don't have a good gradient of your fitness with each successive generation, you need to know how to tune the evolutionary algorithm in order to get better results from it. As every automation, it's time and resource consuming, so you need to be careful when you try to apply this approach. It should be justified, and if the conditions are not the right ones, probably it's not a good idea to bother with this. And also your convergence, or the fact that your fitness function is able to drive the selection in the direction of your goal, is not guaranteed. It basically depends on your skill and the data that you are able to collect and interpret properly. So if you're not able to achieve that, you won't be able to get successful evolutionary testing. So finally, this is just a quick list of good open source software which could be used for implementing such an approach. The first one is named Evolutionary Computation for Java. The second one is Evolutionary Objects, the one that I mentioned that we used into the example, which also has a successor which is named Paradiseo, which is actually a multi-objective framework. It can actually work with multiple goals and optimize simultaneously for them. And the last one is again a multi-objective one. As you can see, they're either implemented in Java or C++. This is not the only implementations that you can come across, but probably the best examples that I can give you, especially the first one. As you can see, most of them are active projects in most cases. They can work with custom implementations of evolutionary algorithms. You can use pre-built implementations of evolutionary algorithms and customize them. Most of them are compatible with distributed execution, and especially in the first case, they have a very good documentation which can guide you and give you the details about how we can work with this kind of technology. So this is all that I wanted to share with you. So if you have any kind of questions, I'll be happy to answer them. Anyone? Well, because I know that we are supposed to have a lunch break, so if you feel that you want to ask me something, I'll be around at the Experience booth. So if you want to ask me something or discuss something, I'll be happy to discuss this, and I don't want to keep you any longer. So enjoy your lunch, and afterwards, if you have any questions, I'll be happy to answer them.